Okay. So let's just keep going here and let me share my screen again. Oh, all right. I'm waiting on PowerPoint again. I'm not sure why this is so problematic. Let's try. Okay. All right. So hopefully you're seeing my slide deck now. And so we just finished talking about the DSRC and some of the issues here, and noting that kind of the biggest issue that has hurt the deployment of this technology that should save lives is, of course, cost, both in terms of capital equipment expenditures, needing to put these RSUs out there, and then the operating expense. Someone's got to maintain those, provide power to them, repair them, and so on. Right. So there's both capital, CapEx, and operating expenses, or OpEx. So then we have kind of maybe the newcomer. Depends on when you want to, how you want to write the history, but instead of being Wi-Fi inspired, now it's going to be cellular inspired. And so we talk about a C-V2X, and this is supported by the 3GPP. These are the folks that are the World Standards Organization for LTE, 5G, soon to be 6G, so on, both in future and in the past. And so this is being developed. It's still evolving. We kind of have an LTE V2X, but we're also developing a new radio, or 5G. So this is more like 4G. This is more like 5G, but some of these G's are pretty broad and coarse, right? So even within 5G, things evolve, right? And they evolve through these release processes with the specs, the standards. And so to give you an example here, here's one part of the standard. And so here's the 5G architecture enhancements for 5G systems, 5GS, to support vehicle to everything services. And this is part of the 3GPP system, and it's in technical standard or spec. I think it's technical standard is what it stands for, but it's just TS 23.287 version 16.4.0 release 16. So these 4G, 5G, 6G standards are produced in releases. And so as you see over here, I've got a draft. So a TR, this is not quite yet at the TS level, but it's still being kind of talked about. And it's TR 37985 version 1.1.0. goes back to 2020-02. This is a technical report, right? And so, but it's still dealing with the same type of thing. Now, in these ETSI 3GPP standards, each little narrow part of this ginormous system gets its own little technical standard or technical report, and it deals with a narrow aspect of it. So you really need to look at a bunch of these. But if you haven't looked at these before, they're an experience. This one is a draft situation, so you got these comments in here and that type of thing. So this will, in some form, probably end up as a technical standard. So, but let me try that. Why isn't it? Does not. From current slide. Let's go. Okay, so all right, so that's just information on how to get to those specs. Then we have oh, come on. There's two big modes that are supported. We have this UU support where the user equipment, it might be a radio, cell phone radio in your car. It's not necessarily the one you're using, but it's built in your car, your autonomous vehicle, whatever, right? And it's connecting to the base station just like your normal cell phone does, right? And then if it wants to communicate with someone else, it's going to go to that base station first, and then that base station is going to transmit that information out. There's another mode, which is this PC5, where you're able to connect directly with other vehicles. Well, call it connect, but not really, right? Because there's not a hard or a connection established. You're more just broadcasting, right? So, but you're talking directly to other vehicles, right? So in other words, it's infrastructureless, right? And so this can be used out of coverage area. So we've got a lot of base stations, particularly on our highways. Coverage is okay. You get up in the Adirondacks or something like that, or Catskills, you're going to lose coverage. There'll be plenty of areas where you're outside of coverage, even on the highway, right? But most part, we've got good coverage on our highways. But even when we don't, we can use this PC5 in an infrastructureless mode. So here we're going to use this EMBMS. It's a multicast type system that's part of the 3GPP, and it's kind of bigger than just this V2X type system. It's used in other areas, but you can either broadcast information, which is rarely used, or you can multicast to a certain group of radios, right? So, and it's designed to be very efficient. So, and that's used to send all that vehicle status info. So all the things we talked about from the previous, the RS, DESRC, it's sending out that vehicle status information. So we're going to use this EMBMS to do that. This is at a much higher data rate, right? 5G is designed for, has wide bandwidth allocations typically, and so it can support very high data rates, particularly if signal noise ratio is good, if you're near the transmitter as a receiver. So it's much lower latency. There's not one number to quote here, but you can be dealing with 4 millisecond latency. It's super fast, right? But typically, 20 milliseconds for a pre-crash sensing scenario, maybe much longer for other type of scenarios. Maintaining a low latency is expensive because it kind of precludes other type of communications going on. So you don't necessarily want to have all your traffic moving at this low latency, or you're not going to get there, right? So you're going to use your kind of high priority, urgent messaging for this low latency, and let other things go at a higher latency. Lots of trade-offs there in terms of how you packetize your information and stuff. But here now we're able to support 350 kilometer per hour mobility support. Of course, this is not just for cars, but it could be supported on high-speed trains, or that type of thing, right? So it's also much more scalable, because there's some support for scheduling transmissions, particularly if you're going through the base station. The base station is a scheduler, and it determines when everyone gets to speak, right? So it's like, okay, you speak, now you speak, now you speak, right? So that requires a lot of infrastructure and some handshaking, some control information going back and forth, but it's really drastically minimizes these collisions, and because really only one person should be speaking at a time, right? Only one radio transmitting at a time. So you're not going to have this collision system where you first have to detect that there's a collision, and then you have to back off some random amount and then try again, and that type of thing, right? So everyone's kind of scheduled now. So it's much more scalable. We can handle lots more number of vehicles. The infrastructure, well, if you're using this UU mode, you're going through a base station. That's infrastructure, right? It's a big tower, much more expensive than a Wi-Fi router, right? But it's all that infrastructure now is supported by a diverse set of users and business models, right? Yeah, sure, you've got a tower, you've got radios, you've got antennas, you got to have power brought to that tower, you've got to have some maybe possibly air conditioning to keep your electronics from burning up, and you may have a fiber run for backhaul, connect to the internet or the rest of the network, that type of thing, right? But of course, we're spending a ton of money each month on our cell phones, right? So we're paying for that. Someone's already paying for that. So the incremental cost to support this V2V type application is small, right? Now, there are some synchronization issues because we're having this scheduling type of situation, and even if we're communicating directly with other vehicles, there's some synchronization that needs to go on in order to get to this 1 gigabits per second. And that's an area, if you're interested in it, it's fascinating. You can get synchronizations by connecting to a base station or from a GPS or GNSS type satellite. If one side of this connection, this PC5 connection, has access to a base station, but other radios don't, then they can kind of share the synchronization issues, information. But we want to be synchronized so that we're all kind of talking at the right time, and we're not talking on top of each other. So here's kind of a classic diagram that you see in these standards and papers that are written about the standards and that type of thing. But all of these signal paths are labeled using these mostly cryptic type of nomenclatures that, when you work on a certain area of 5G, you start to get to know S1, V3s, whatnot, right? But here we have a user equipment A particular vehicle, right? UE stands for user equipment. In older days, we call them subscriber units, SUs, but here we have another one, right? So these are peers of each other, and we see that they talk to each other potentially over this physical layer PC5 kind of connection, right? It's a lower level, not necessarily right at the physical level, but then we can have kind of stacked on top of this vehicle, it's running some one or more V2X applications, right? And this vehicle might have the same type of V2X application. That connection we call a V5. Now it's really, if you study networking, it's kind of a higher layer. It's at the application layer, but the packets that are going back and forth on these applications are still traveling over this more physical link here, right? Alternatively, we're connecting to the infrastructure, right? So this is an LTE type thing rather than 5G, but so some of the nomenclature looks a little bit different, but this is a EU trans. So now we're connecting through a base station, and then that gets connected to maybe a V2X application server. Maybe this thing is gathering up a whole bunch of traffic data and then sending it out through this V2X control function, right? So the main thing to pick up from this is that there's a possibility to go infrastructureless and talk directly to each other. And generally, that's maybe I'm making a big statement here, but for a lot of these messages, UEA is just kind of broadcasting its information during its allocated time slot, and UEB is transmitting its information at another little time slot, frequency slot. As it turns out, in OFDM type communications, there's a frame in which we transmit that has a bunch of different frequency channels and different kind of slots in time. So a UE, whether it's your handy cell phone or whether it's a machine like a vehicle, is going to be allocated some number of these slots to talk in, sometimes called a resource block. And so that's all kind of allocated in this infrastructureless system that kind of has to be negotiated between the UEs, but in an infrastructure, when you're talking to the base station is controlling that, right? And so so UEA is broadcasting its information, UEB is broadcasting its information, and they're both listening to each other, right? But not necessarily a full-blown connection set up like you would on a call when you call your friend or something, right? So this PC5 mode that we're talking about has two different sub-modes associated with it. I don't know what they're called, but they're called modes, but this is also called a mode or channel, I guess. So we have mode 3 and mode 4. I don't know what happened to mode 1 and 2 or whatever, but mode 3 and mode 4 are the ones that we're concerned about. And mode 3 is where we're scheduled. So you're also going to see the term side link used with this PC5 mode, where instead of we're going to a base station, we're just kind of linking off to the side to other peer users, right? So side link is the term used there. And so in mode 3, now we're going to allocate these slots to user, the resource assignments, the frequencies and time slots to use is going to be allocated by this base station controller. We call that eNode B, enhanced node base station. I don't know. Some of these things go back generations, and they keep there's a lot of legacy associated with some of these terminologies, right? But so if you can connect, you're in coverage area and you can connect to the base station, then the base station will take on the role of allocating things, right? And tell which card to use which of these resources, right? Spectrum, time and spectrum resources. And this, of course, requires a cellular infrastructure support for this radio resource management. But that's kind of easy to deal with, right? But if you're not in a coverage area, if you're outside a coverage area, you cannot connect to a handy base station controller with its sophisticated scheduling software on it. Then you go into this mode 4, this autonomous mode. Now your resource and interference management is performed by the vehicles in a distributed manner, right? So they kind of collaborate and decide who's going to talk when and where in terms of spectrum, right? So again, you don't want people talking at the same time on the same frequencies. Right? They can talk at the same time on different frequencies, or they can talk on the same frequency at different times, or they can talk on different frequencies and different times, right? But they can't talk on the same frequency at the same time, because then we end up with interference and stuff. So there is a mode, this mode 4, this is autonomous mode, to be able to handle that situation where we don't have this kind of centralized, almost omniscient. It'd be nice if it was omniscient, but the kind of all-knowing E-node B to allocate everyone out. So, all right. So to wrap up then, so this is this new radio V2X potential. That's kind of the 5G and maybe eventually 6G system, right? So enhanced bandwidth and range make it possible to share intention information, in other words, trajectory. So there's a 5G Automotive Association, 5G EAA, an industry group. It claims that chipsets are already ready and performance is ready. They've done some trials in Michigan. I think 5G EAA is based out of Detroit, Michigan. Others are maybe more skeptical and expect wide deployment more in the 6G and the 2027, 2030 timeframe. So let's look real quick at 5G AA. So you can go there, and if you're interested, and kind of dive into that and get some more details about things, or we can. Let's see, do I still have that up? Well, I had here it is. Okay, sorry. So just so happened that today I listened to a webinar from Dr. Jeffrey Reed from Virginia Tech, as a distinguished lecturer for the Future Networks IEEE working group. And he actually talked about 6G. Right? So now we're dealing with 5G, and I'm talking cell phone technology, right? So there is a Wi-Fi 6, so 802.11 type stuff. We're already in Wi-Fi 6, and now we're looking towards Wi-Fi 7. But in the cellular world, we're currently working with 5G and looking at 6G and stuff. So here's some time frames on that. So we're in this region right now, and wrapping up things like release 17, release 18. Actual hardware tends to lag behind. Hardware and applications lag behind a little bit, of course, but 6G is looking here in this 2027, 2030 timeframe, right? And so there's a lot of new things coming in here, and a lot of, as you might expect, everything is AI and ML these days, right? And but here's that side-link relay. Here's so there's some satellite, uncrewed aerial vehicles, vehicular communications. And he puts this comment on here on a slide deck. Yes, 30 years late, right? So remember that DSRC or DRSC, whatever, started back in the late 1990s. I think 97 is when they actually started, and maybe 99 is when it got allocated and stuff. So, and he's predicting that this is actually going to come to fruition in the 5G advanced 6G timeframe out there 30 years later. So don't hold your breath is kind of what we're saying there, right? So all right, let's look at some applications of other type of vessel types, right? So so this will be our last new material we look at, and next week I will do a semester review, right? So it's been kind of hard because so many of these topics are kind of disjointed. Yes, we did have kind of several weeks of machine learning there, but even that was a little bit disjointed, and we went through everything really fast. So I'm going to spend next week just kind of reviewing everything. Hopefully talk a little bit about some new research areas, or maybe I'll cover that here in a few minutes. But we'll look here at application to different vessel types. Of course, we spent so much of this course talking about the kind of canonical use case of the robotaxi, right? Not restricted to that, but a lot of the things are associated with that. Autonomous vehicle, no driver. Yeah, we call it unmanned, but there's possibly passengers in there, maybe some freight. But it's a road vehicle designed to run on highways or city streets. And we're dealing with traffic signs, the stoplights, and other road users and that type of thing. But if you're dealing with autonomous vehicles, you don't have to restrict yourselves to that. So let's take a little bit of time to look at maritime issues, some aerial. We're pretty familiar with that. I mean, we've kind of been dealing with aerial drones for longer than we have autonomous vehicles in the public's sphere of things, right? So at the consumer level. Touch on subterranean space and agriculture. Really, all I'm going to do is highlight some of the issues that we need to look at, right? So, all right. So, yeah, let's put this thing on a ship, right? So that we're looking at doing this for both freight type ships and warships, right? So, but regardless, there's no roads to follow, right? There are buoys, day marks, etc., different things to interpret and follow that are typically near shore at inlets, at harbors that show you where maybe reefs are, or rocks, or things to stay away from, right? And we do have charts, navigation equipment, and technology that shows us where the deep water is, where the shallow water is that we want to stay away from, and that type of thing, right? And then we have this coal regs, right? 72 coal regs, but it's the International Regulation for Prevention of Collisions at Sea, written in this case in 1972, that version, and also the U.S. Inland Navigation Rules, or these are rules of the road, right? So if you have spent much time on a boat, then you may have learned that, like in command of a boat or something, that there's still rules of the road, right? If we're driving a vehicle, a car in the United States, we're going to stay on the right-hand side, and we're not going to cross the solid yellow lines and that type of thing, right? So at sea, you have to have some sort of known way of arbitrating who's got to give way to another boat, right? So, and that's included in these coal regs. So, like a boat under sail has kind of privilege. That's the wrong word to use legally, but a motorboat has to give way to a boat that's only under sail, right? Or you have to give way to a tug that's towing a barge, or a dredging machine, anything that has limited mobility. And if you're approaching at right angles to each other, there are certain rules on who has to give way and who should continue on their way, right? So, but there's not lane markings. There's no signs out there other than a few of these buoys and day markers, right? Add to that you've got to deal with currents and wind. If you're navigating a boat, whether you're manned, it's a manned vessel or it's an unmanned vessel, currents and wind take you in different directions and you think you're going to go, right? So you have to account for that. And then the other thing is this long duration, right? So, and you need to be able to kind of sustain that power plant challenges. You look at these big boats, they've got a whole crew that's manning the engine room, and they're managing those engines. And in fact, the DoD just released their Small Business Innovative Research Grant topics today. And I was looking in here, and the Navy has a topic that is has the objective to develop and demonstrate a megawatt scale, ultra high reliable and efficient unmanned surface vessel modular generator concept configured with smaller kilowatt scale building block power units and a high density package to achieve a 4,000 hour no touch maintenance periodicity. You're not changing your oil, you're not changing the air filter, you're not doing anything on this. You're not adjusting the injectors, right? So, you know, you might just toss a diesel engine at these things, but your maintenance interval on a diesel engine is going to be typically 100 hours when you change an oil or something, right? So now, if we really want these things to be unmanned and be able to go out in blue water, whether it's kind of a Navy DoD type vessel or a tanker or a freighter, a container ship or something like that, then we need to tackle this maintenance problem. The Navy has been trying to go with a lower manned workforce on ships for a long time, and they've gotten into trouble with that, trying to do kind of this generational literal warfare ships that were developed in the 2000s and 2010s are already being decommissioned way before their expected lifetime, because they just did not live up to the promise of being able to be maintained in operating condition by this small manned workforce. So it's a big problem, right? So there's a research solicitation looking for small companies to try to solve that problem. So all right. So some of the applications, right? So just to look at the kind of DoD type things. One is for missile tubes, right? So our historically carriers, cruisers. I have carriers there. That's the wrong term. Cruisers are kind of the largest non-carrier ship, right, in the Navy, and destroyers and frigates, but cruisers are the ones that really had that offensive capability of launching missiles, whether they're to do an offensive engagement or to let's say ship-to-air missiles or ship-to-ship missiles to protect the carrier that they're responsible for. So our carriers are getting old and they're going out of commission. We don't have ships of that same class to replace those. So there's some concern about how do we be able to deploy enough missile tubes to be able to launch enough missiles to sustain a conflict that we find ourselves in, right? So it could be security patrols here. We can look at a couple of these here. Well, it's been a while since I looked at these, but here's a drone boat leading Navy ships in the Straits of Hormuz, sign of things to come. So here's an autonomous vehicle right here, trying to protect. I think that looks like that might be a destroyer or a cruiser over there. And so here, obviously a photo op, but we've got a unmanned autonomous vehicle being operated, or semi-autonomous drone boat there. Then we have port security. This is an older SBIR, wow, from 2019. And again, this was a solicitation, and it's designed for unmanned surface vehicle and underwater vehicle autonomous behavior development and stuff. So if you're interested, you can dive into these things. Here's another one that was unmanned harbor poly team and stuff. So supply chain delivery of supplies, or potentially even as a weapon, as we've seen in the Ukraine-Russian war that's going on right there, where they're not quite fully autonomous, more remote controlled from what I've been able to see and stuff. But we're learning that these are, whether we like it or not, are going to be used as weapons of war. So we can also go underwater. And of course, we've had remotely operated vessels and submersibles. These have been around for years. Oil industries used them. They found the Titanic using these things, that type of thing. Autonomy can supplement these type of things instead of having to be remotely operated. And you have the advantage of being long duration. But navigation issues, power issues, some of these are designed to surface and then get a location fix, maybe communicate, maybe recharge. There's been a lot of research. Can you scavenge some energy from wave motion on these things or whatnot, right? So mine detection and demining is an application here. Lots of applications with submarines, and some we can't talk about. So all right, so then let's leave maritime. Let's go to aerial. I think this is something we're probably more familiar with. A lot of us have played with drones before, even way back when. The drones were designed with a GPS receiver, and when you would take off, they would take a fix and say, this is my home base. And if I lose communication, then I'm going to try to return back to that base, right? And or at least to just land in a safe manner, right? So there's always been, for the higher end drones, some little bit of autonomous behavior. We've seen swarms. There's swarms for entertainment purposes that are trying to replace fireworks. that do all sorts of pretty designs in the sky. And there's some more sophisticated uses of swarms also, right? And there you can imagine that there's a little bit of that kind of concept of that leader-follower type of thing, where they're trying to position themselves relative to other drones and stuff. So we have this autonomous mode when comms are lost. And then we can look at more of the fully autonomous type of things. Of course, we've seen some of these applications talked about, whether it's an Amazon or someone's delivery drone, search and rescue, agriculture, construction, industrial power line monitoring. So you have these high voltage lines that go for many miles. They need to be periodically inspected. It's expensive to do that with a helicopter. It's maybe not that effective doing it with trucks. Difficult to do that also to get to them sometimes. So drones are being used to monitor power lines, look for issues, hopefully before they cause some horrible fire like we've seen out in California, or a big outage or something like that, right? Security and surveillance are big issues, mapping and photography, and as we've seen, weapons delivery. So here we can look at some FAA regulations. This is really more of a newsroom memo about the regulations, but you can follow it, get right to the code of federal registers or regulations, whatever CFR stands for. And but there's, the idea is, all right, so if you want to fly a drone, then you should do it in daylight, and always keep your drone within sight. Only do one drone at a time. Don't fly over people. All right, so what about all these other things where they're autonomous? Well, you can ask for waivers, right? So that's kind of where we're at on these things. So there's a lot of information here, but you can do this. There are exceptions, but it's still an evolving regulatory environment. All right, let's look at subterranean type issues. Here, you might run into this in a search and rescue type situation, but there's also there's another war going on right now in Israel and Gaza, and there's a lot of tunnels involved there, and so we've faced this type of conflict to a degree before. I know that there's the military is always concerned about being able to explore bunkers and tunnels and that type of thing in a safe manner without putting our soldiers in too much danger. Obviously, being a soldier is a dangerous profession, but we try to develop technology to minimize their danger, right? So these are great places for an adversary to hide and operate. The Defense Threat Reduction Agency did a research solicitation on doing federated reinforcement learning. So various drones could explore an area and learn how to go through that using reinforcement learning. But then federated part means that they're sharing that information with each other. So you might have several different drones, and each is exploring a certain area of it, but they communicate that information and learn together, right? So obviously there was a thing, I think in India, was it, where it was a horrible mining accident. Fortunately, I think everyone got out safely after over a week being trapped in there, but lots of issues. So the big challenge here is location localization. You don't have GPS in a subterranean situation. You have potentially very difficult visual conditions. You may not have easy, smooth surfaces to go on, so you might have some mobility challenges. You might not have a good map of it, so you might be doing that simultaneous location and mapping type algorithms that we ever so briefly talked about kind of after that particle filter, Kalman filter, particle filter lectures, right? So, all right, then in space, we've got our own set of situations. So, we'll talk a little bit about Space Development Agency. That's, again, a U.S. DoD type agency that is trying to, from space, solve kind of the challenge that's presented by some of the hypersonic missiles that are potential adversaries of the future might have and use against us. These are missiles that are moving extraordinarily fast and are difficult to deal with just from the surface, whether it's the ocean surface or land surface. So Space Development Agency is deploying these overhead persistent infrared sensors in what we call proliferated low Earth orbit. So they're a couple of 100 miles up, and there's a bunch of them, kind of like a Starlink constellation, except they're designed to stare down and look for heat signatures. So that hypersonic missile, not only are you seeing the heat from the rocket engine, but even after that has shut off and it's coasting through the very, very high upper atmosphere, and as it re-enters, it's going to be generating lots of heat. So so it's easy, but the time is a very pressing factor, right? So we're not really putting up autonomous motion and that type of thing, but it's just the idea of putting autonomy up there to be able to attack, track, and target these hypersonic missiles, and then be able to relay that information right to commanders, or even potentially to, let's say, an F-16 or something that's on patrol to try to defend against. So it's a very different application than what we're talking about, but it's using a lot of the same technologies that we've looked at. So I just mentioned that. And then something I mentioned before is NASA planetary operations, right? So NASA, we know, we've gone to Mars, we're trying to go back to the moon. Mars is really tough because we've got round trip communication latencies between 8 and 48 minutes, depending upon our relative positions in our orbits, and between Earth and Mars. So it's a long time. So we also have extremely limited data rates with link budgets requiring sophisticated forward air control, just because it's so far, right? And we're energy constrained, particularly in space. And so we can't really use human in the loop real-time control to drive fly a helicopter or drive a vehicle, that type of thing, right? So in the past, everything's been very, very carefully planned out. And we move that crawler rover a short distance, and then we would look again and do a whole bunch of planning and that type of thing, right? So, but we're doing, you start flying a helicopter, and now you've got to be able to make many more decisions locally and in real time. And of course, then it's like, can that autonomy be trusted? It's not like you can send a repair tech out to press the reset button on the system. So it's got to be right. And NASA has a big need for autonomy, and they work really hard at it, but they're also very, very conservative about deploying autonomy, because they want things to be able to be provable that it's going to work and that type of thing. Autonomy is hard in that aspect. All right, and then finally, you've probably seen these things that hit the news media over the last maybe 2 years, maybe 3 years, the weed zapping with lasers type of thing that goes down a field. And that's pretty cool because we could maybe drastically reduce herbicide use and end up with healthier food and healthier ecosystems because of that, right? So there you're moving down a field, which is not the hardest thing in the world to do, but you've got to recognize weeds. So there's a computer vision object detection type thing. You need to recognize a weed from a beneficial plant and be able to localize it so you can target it and zap it. And then there's even rock clearing, similar type of thing, but now we're trying to clear a field with rocks and just minimize the human labor required in that. But we've had precision agriculture for a while now, right? So I'm here in the Midwest, and we've got John Deere and that type of thing in the Midwest, and they're developing these super high-end modern tractors that essentially drive themselves. The farmer sits in there and monitors the thing, but they set it up, and the tractors keep historical information and know parts of the field that have high yield versus low yield, and can dose chemical treatments. And right now we're back to chemicals in our agricultural system, but at least if you can add in this precision agriculture concepts and know this part of the field doesn't need that much fertilizer, herbicide, or pesticide, then you don't put that much on there. But other parts of the field maybe are suffering, and you add it there. So it's instead of having to put in a whole bunch to take care of a problem that may or may not be a problem everywhere in your field, you're only putting out what you actually need. So maybe not optimal, but better than the alternative, right? So so that's it. Let's see, is there anything else that I can show you here? I think I've covered most of the stuff that I had. Oh, we can actually look at a few more of these topics. What time is it? 8:02. And I won't take too much of your time and let you go, but I went through these different topics. You can see there's 185 of them open, and they're for all sorts of different things. And these are set-asides for small businesses, or in some cases, collaborations between a small business and a research organization like the university or college or so. But here's another one from the Navy: multivariable unmanned anti-submarine warfare system assessment and optimization toolkit. So here's a system that is basically going to be a software system that the Navy can use to kind of design and optimize unmanned anti-submarine warfare platforms, right? And talks about different trade-offs that they might be interested in, the self-noise versus endurance versus operating speed. Obviously, if you want to go fast, you're going to generate a lot of noise. If you go fast, your endurance is going to go down. Just like if you drive 80 miles an hour on the freeway, you're going to burn more gas per mile than if you went 50 miles an hour on the freeway, right? Payload capacity, all these different trade-offs, right? And then so they want to have a system that helps them trade all of that off. So not exactly research in autonomy itself, but all around it, right? And understanding that aspects. Here's another one, a common software platform for learning-based robots. Here they point out that there's been a lot of rapid research to production for lots of AI things, and you know, we know these, right? So computer vision, natural language processing, you know, chat GPT and stable diffusion and that type of thing, right? All this generative AI is released, and then people are using it in business and applications right away. But they're claiming that reinforcement learning, in particular, that's associated with robotic hardware, it's just not happening, right? So they're looking for ways to kind of figure out how to bridge that gap. And you see they've referenced, as it turns out, a couple of things that we've looked at here. This ROS, this Moose IVP, we talked about both of those in our edge computing lecture a couple of sessions ago, right? So there you go. And let's see. Oh, here's another one. Soft robot for locomotion in granular seabed media. It's again a Navy one. This T means it's a collaboration set aside for a collaboration between a small business and a research organization like a university. So this is interesting to you. You're early in your master's program. Maybe you work with your advisor and you go find a small business and you write a proposal for this, right? But this is develop a soft robot. You know, think like something modeled after a octopus or something, right? A soft robot capable of untethered autonomous locomotion within granular media, think sand and stuff in shallow sea floor environments, right? So I think there's a few more here. Special Forces Command, small unmanned ground robotic systems, right? So and they want to be able to control this using a little robotic grip kind of game controller type of thing, or from this TAC thing, which is essentially like an Android phone app type of thing. Obviously more secure than that. Oh, here it is, Android Team Awareness Kit and stuff. So be able to control a ground robot. Silvus Technologies is a major manufacturer of radio communications, so it's got to work with them. So yeah, same thing with persistent systems. So you can imagine that SOCOM Special Forces uses these things in various different ways, right? So I think there might be one more I flagged, or was that it? Maybe that's it. So all right. So let me stop sharing. So that's the end of our lectures. Again, next week I'll go through and try to highlight what I've would think are the things to take away in this course. I'm trying to find my camera here. And stuff, and kind of review. I hope you still show up for that. But also make sure that you're wrapping things up. Please, if you're stuck on your project, there's not a lot of time left, but get in contact with me. Set up a meeting. This week is better than next. Time's running out next week. But let's get that done. Let me help you with your project. Let's get it done. I'd love to give everyone A's in this course. So I'm going to help you get there. Ultimately, you're the one that's got to put in the work, though. So, all right. Take care. I'll stop recording.